It's a pleasure to have you all here with us. So today we have the pleasure of having Professor Paul Terwilliger with us. He's a very well-known mathematical physicist. He received his PhD from University of Illinois Urbana-Champaign, and he's been a full professor at University of Wisconsin-Madison since 1994. And he's one of the leading experts in the areas of combinatorics, algebraic graph theory, and many other things, including like quantum groups and quantum Lie algebras. And today he's going to talk about the alternating central extension of the Onsager algebra. So go ahead, Paul. Thank you very much.
Okay, thank you very much. So I do appreciate the invitation, and I'm delighted to be here. Okay, so the title is the Alternating Central Extension of the Onsager algebra. Okay, let me give you a quick overview. So that Onsager algebra, OQ, is a quantized enveloping algebra for the Onsager Lie algebra. And recently, Baseilhac, Koizumi, and Shigechi introduced an algebra, Caluq, called the alternating central extension of OQ. And in this talk, our goal is to describe how OQ is related to Caluq. And to motivate the description, we're first going to consider a toy model involving the positive part, UQ plus, of the quantum group UQSL2 hat, and its alternating central extension, Caluq plus. And we'll see that OQ is related to Caluq in essentially the same way that UQ plus is related to Caluq plus. Okay, a few quick preliminaries. Recall the natural numbers, 0, 1, 2, and so forth, and the integers, and let F denote a field with characteristic 0. Every vector space and tensor product that I discuss is understood to be over F, and every algebra without the Lie prefix mentioned is understood to be associative over F and have a multiplicative identity. Affix a non-zero Q in F that's not a root of unity, and recall the notation, the bracket n sub Q notation, Q to the n minus Q to the minus n divided by Q minus Q inverse. Okay, now our story begins in statistical mechanics. In 1944, Lars Onsager calculated the free energy of the two-dimensional Ising model in a zero magnetic field. And in his calculations, Onsager introduced an infinite dimensional Lie algebra now called the Onsager algebra. And we'll denote that Onsager Lie algebra by O, capital O. Okay, here's the definition. So the Lie algebra O has a basis, A sub k, k an integer, B sub k plus 1, k a natural number, such that for all k and L, the Lie bracket of AK and AL is twice BK minus L. The Lie bracket of BK and AL is AK plus L minus AL minus K, and the B's mutually commute. And that basis, we'll call that the Onsager basis. In the literature, this essential basis takes slightly different forms depending on what normalization you're using. So what you see here might look a little bit different from what you're familiar with, but it's essentially the same thing. Okay, anyway, that's the Onsager basis. Okay, a few years pass. Perk, 1989, obtained a presentation of O by generators and relations. So the presentation has two generaters, A0 and A1. And the two relations, as you see there, the compound Lie bracket A0, 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 A1 is equal to 4 times the Lie bracket of A0 and A1. And then the same with A0 and A1 interchanged. So those relations are called the Dolan-Grady relations. Okay, next I'll recall an embedding due to SS Rohn of the Lie algebra O into the SL2 loop algebra. Now first I'll define a few concepts. Let's just recall what is SL2. So Lie algebra SL2 consists of the 2 by 2 matrices over our field F that have trace 0, together with the Lie bracket given by the commutator, brackets RS is SRS minus SR. Okay, and SL2 has a basis consisting of a matrix E, 0, 1, 0, 0, F, 0, 0, 1, 0, and H, 1, 1, 0, 0, minus 1. And the Lie bracket of H and E is 2E, H against F is minus 2F, and E against F is equal to H. Okay, now I'll bring in the loop algebra for SL2. So from now on, T will be an indeterminate, and F brackets TTN will denote the algebra of Laurent polynomials in T that have all coefficients in F. And now let L of SL2 denote the Lie algebra consisting of the vector space, which is the tensor product of SL2 and this Laurent polynomial algebra, with the Lie bracket given as you see there, the Lie bracket of U tensor phi against V tensor another phi is the Lie bracket of the U and the V tensor, the product, ordinary product of the two phi polynomials. Okay, that L of SL2, that is the SL2 loop algebra. Okay, and then according to Rohn, there exists a Lie algebra homomorphism from the Onsager algebra into this loop algebra that sends the A0 element to the 0, 1, 1, 0 matrix, and A1 goes to 0, TT inverse 0. Okay, and then that homomorphism sends the Onsager basis elements, the AK and the BK, to the matrices that you see there at the bottom. Okay, it turns out that that homomorphism is injective. Okay, now let's turn our attention to algebraic graph theory. Now, you don't have to be an expert on this to understand this part. I'm just going to give the gist of it. So in 1973, Philippe Delsart introduced the so-called Q polynomial property for distance regular graphs. Okay, a certain kind of highly regular graph. Okay, and over time, this property was studied deeply by many people such as Banai, Ito, Leonard, Cameron, Utals, and Seidel. And building on the work of all these people, in 2001, I introduced the notion of a tridiagonal algebra. And this algebra is defined on the next slide. It goes like this. Start with some parameters, some scalars, beta, gamma, gamma star, rho, rho star. And then the corresponding algebra T is defined by generators and relations, two generators, A and A star. And the relations are as you see there. Let's look at the first one. In the top line, we see 4 terms. Each term involves three A's and an A star. And as we go from term to term, we're essentially sticking in the A star, in between the A's in all possible ways. Okay, and we're throwing in some coefficients. And on the right-hand side, we have some lower order terms. Okay, that's the first relation. And the other relation is just the same with the A and the A star interchanged. Okay, that algebra T, that's the tridiagonal algebra. And those relations are the tridiagonal relations. Let's look at some special cases. So first example, suppose beta was 2 and the gamma gamma star are 0 and the rho rho star are 4. Then those tridiagonal relations become exactly the Dolan-Grady relations. Triple commutator A star is 4 times A star, and the same with A and A star interchanged. So in this case, the T becomes the universal enveloping algebra, U of O, for the Onsager Lie algebra O. Okay, next example. Suppose beta was q squared plus q to the minus 2, gamma gamma star is 0, and rho rho star are also 0. then the tridiagonal relations become the Q-ser relations, as you see there, bringing in now a Q commutator of, defined near the bottom there. You see the Q commutator of H and K is QHK minus Q inverse KH. So with that in mind, we have the compound commutator A star sub Q, Q inverse, and plane equaling 0, and then the same with A and A star interchanged. If you expand those compound commutators out, you will find the familiar Q-ser relations of cubic type. Okay, anyway, so in this case, T becomes the positive part, UQ plus, of the quantum group UQSL2 hat. Okay, one more example. Suppose beta was Q squared plus Q to the minus 2, gamma gamma star are 0, and the rho and rho star are something non-zero now, minus quantity Q squared minus Q to the minus 2 squared. And in this case, the tridiagonal relations become the Q-Dolan-Grady relations, as you see there. So left-hand side, just like the Q-ser relations, but now on the right-hand side, we have a scalar multiple of the commutator of A star and A for the first equation, and similar for the second equation. Okay, so in this case, T becomes the Q Onsager algebra OQ, the star of our show. Now that Q Onsager algebra OQ is, think of it as the most general kind of tridiagonal algebra, at least up to normalization. And like I mentioned earlier, we'll view OQ as a kind of quantized enveloping algebra for the Onsager Lie algebra O. And our broad goal is to understand OQ as best we can. Now we'll investigate OQ using the following strategy. Our experience suggests that whatever happens for O and UQ plus, something similar happens for OQ. But the algebras O and UQ plus are much easier to understand than OQ. So we'll use our understanding of O and UQ plus to make some educated guesses about OQ. In other words, we'll use O and UQ plus as toy models for OQ. Now, earlier we gave a basis for the Onsager Lie algebra O, called the Onsager basis. It's a natural problem. Find an analogous basis for UQ plus and OQ. Now, for UQ plus, such a basis was already found by Damiani around 1993. And her results are summarized on the next few slides. I'll be talking about PBW bases. Let's just recall what that's about. Suppose Cal A is just any algebra. Okay, so I'll be talking about this Poincaré-Birkhoff-Witt, or PBW basis for A. It consists of a subset omega of A and a linear order on omega, such that the following is a linear basis for the vector space A, the set of all products A1, A2 out to AN, and a natural number where the AIs are in omega in order. Okay, now in 93, Damiani obtained a PBW basis for UQ plus involving some elements that she called En delta plus alpha naught, okay, n0 to infinity, En delta plus alpha 1, n0 to infinity, and En delta, n1 to infinity. Those subscripts, the n delta plus alpha naught, alpha 1, etc., those represent roots, real and imaginary roots for the Lie algebra SL2 hat. We don't have to get into that. It's just some indexing set as far as we're concerned. Anyway, these elements are recursively defined in the following way. The E alpha naught is just the A generator. The E alpha 1 is the A star. The E delta is up to a scalar, the Q commutator of A and A star. And then for n positive, the En delta plus alpha naught, En delta plus alpha 1 are given by the recursion that you see at the bottom there. Okay, and then the En delta at the very bottom, kind of Q commutator. Okay, anyway, so by this recursive procedure, the En delta plus alpha naught and so forth are generated. Okay, then according to Damiani, a PBW basis for UQ plus is obtained by those elements, the En delta plus alpha naught, En delta plus alpha 1, En delta. In the linear order I'm specifying, you go through the En delta plus alpha naughts in order first, followed by the En deltas in order, followed by the En delta plus alpha 1s in reverse order. Okay, now in 2020, the physicist Pascal Baseilhac and the mathematician Stefan Kolb obtained a PBW basis for OQ that's analogous to the Onsager basis for O and the Damiani PBW basis for UQ plus. And their results were motivated by the theory of quantum symmetric pairs. And the results are summarized in the next few slides. So the Baseilhac-Kolb PBW basis for OQ involves some elements Bn delta plus alpha naught, Bn delta plus alpha 1, Bn delta, okay, roughly analogous to the E version. And these elements are recursively defined in the following way. So B delta, just like before, is up to a scalar Q commutator of the A and the A star. The B alpha naught is the A. The B delta plus alpha naught is, as you see there, A star plus up to a scalar, the commutator B delta and A. And then for n at least 2, the Bn delta plus alpha naught is given by this recursion that's somewhat more complicated than what we saw for the Damiani PBW basis. Okay, and on the other side, it's just the same sort of thing. The B alpha 1 is the A star, the B delta plus alpha 1 is just like before with the A replaced by the A star, and so on. Okay, and then the Bn deltas themselves, somewhat more complicated than the Damiani version. It starts off the same, roughly the same, up to a scalar, the Q commutator of the A and the Bn minus 1 delta plus alpha 1. But then we have a sum of products in addition that was not there at the Damiani level. So anyway, it's a little bit more complicated to recursively define this these B's for OQ than it was for the Damiani elements in UQ plus. Anyway, Baseilhac and Kolb managed to prove that if Q is transcendental, then a PBW basis for OQ is obtained by these elements, the Bn delta plus alpha naught, Bn delta plus alpha 1, Bn delta, in any linear order. Okay, now let's come back to statistical mechanics. In 2005, Baseilhac and Koizumi introduced what they called a current algebra for OQ in order to solve boundary integrable systems with hidden symmetries. And they denoted this current algebra by Caluq, but in these slides, I'm going to use the modern notation Caluq. Now in 2010, Baseilhac and Shigechi used an RK reflection equation to obtain a presentation of the Caluq by generators and relations. I'll give this presentation on the next few slides. Okay, it goes like this. So we'll define the algebra Caluq by generators. There's a slew of them, W minus K a natural number, WK plus 1, gk plus 1, gk plus 1 tilde, and the following relations. So for any natural number k, the commutator of w naught and wk plus 1 is the same as the commutator of w minus k and w1, which in turn is equal to a scalar multiple of gk plus 1 tilde minus gk plus 1. And then we see some relations involving q commutators using w naught and w1. Okay, there's more. So in addition, we have all the relations that you see there, each one involving a commutator or multiple commutators. Okay, so infinitely many generators and infinitely many relations as well. So I just defined the Caluq by generators and relations. And those generators, the w minus k, wk plus 1, gk plus 1, gk plus 1 tilde, will be called alternating. And we'll call Caluq the alternating central extension of OQ. And this name will be justified shortly. You might be asking at this point, what's alternating about it? We will see. Okay, now G naught and G naught tilde were not amongst the official alternating generators. For notational convenience, let me bring those in. Those are going to be certain scalars, as you see at the bottom there. Okay, so the next question is, how is OQ and Caluq related? So again, OQ is defined by two generators and these two relations, the Q-Dolan-Grady relations. And Caluq is defined by this infinitely many generators involving the W minus K, et cetera, and infinitely many relations. Okay, how are the algebras related? Well, the first thing found by Baseilhac and Shigechi, 2010, is that for the algebra Caluq, the W naught and the W1 satisfy the Q-Dolan-Grady relations. Okay, there they are in front of us. Okay, so immediately we see that there's going to be an algebra homomorphism from the Q-Onsager algebra OQ into the Caluq that sends the A to the W naught and the A star to the W1. Now, as we'll see, that homomorphism is injective, and not surjective, but that was not obvious in 2010. Okay, forward a few years, in 2017, the relationship between OQ and Caluq was clarified further by Baseilhac and Baseilhac. They showed that the algebra Caluq is generated by its elements W naught, W1, together with the center, Z, of Caluq. And based on the above lemma and their general experience, they conjectured that the alternating generators form a PBW basis for Caluq. And that conjecture turned out to be correct, as we will see. I should mention it's not at all obvious, just from the definition, that those alternating generators should be a PBW basis. I consider it a profound insight that is what should happen. Okay, and it turned out it was exactly correct. All right. Now, anyway, so in 2017, it seemed difficult to understand Caluq. There's so many generators and relations. And to avoid the complexity, we replace OQ by its toy model, UQ+. So our general strategy is to search for an algebra Caluq+ that's related to UQ+ in roughly the same way that Caluq is related to OQ. And in this search, we're going to make use of the Q-shuffle algebra realization of UQ+. Now, this realization is explained in the next few slides. Okay, this Q-shuffle algebra realization of UQ+ It was introduced by Mark Rosso, 1995. And there's also a helpful tutorial by Green. Now for the Q-shuffle algebra, the underlying vector space is a free algebra on two generators. It could hardly be more simple. Now this free algebra, let me describe it on the next slide. Okay, start with two non-commuting indeterminates, x and y. And let bold V be the free algebra with generators x and y. By a letter, I just mean x or y. And for a natural number n, a word of length n in V is simply a product of letters v1, v2 out to vn. The vector space bold V has a linear basis consisting of its words. Now, I just defined the free algebra bold V. So next we'll endow bold V with a Q-shuffle product denoted star. And this Q-shuffle product is due to Rosso. Goes like this. I'll start with special case. Suppose you have two letters, U and V. Then their Q-shuffle product is the free product UV plus the free product VU times a power of Q. The power being either 2 or minus 2, depending on whether U is equal to V or not. So for example, X star Y is the word XY plus Q to the minus 2 word YX. On the other hand, X star X is XX plus Q squared XX, and so on. Okay, now let's consider the Q-shuffle product of two words. Suppose we've got two words, U and V. So we'll work out U star V. Let's write out U and V as a product of letters. U, let's say, is A1, A2 out to AR. And V is B1, B2 out to BS. Now just to illustrate, let's just assume that R is 2 and S is equal to 2. Okay, so U star V is shown near the bottom there, expressed as a linear combination of 6 terms. And those terms are obtained by shuffling the A's into the B's in all possible ways. And we pick up some coefficients. The coefficients are powers of Q calculated in the following way. Every time you pull an A past a B, you throw in a factor of Q squared or Q to the minus 2, depending on whether that A actually equaled the B or not. Okay, and then according to Rosso, that Q-shuffle product star turns the vector space bold V into an algebra. Now, let capital U be the subalgebra of the Q-shuffle algebra bold V generated by the X and the Y. Now, let me just emphasize, capital U is not actually equal to bold V. In the free algebra bold V, X and Y were generators. Bold V is the subalgebra of bold V generated by the X and Y in the free algebra. But with respect to the Q-shuffle product, the subalgebra generated by the X and the Y is a proper subalgebra of bold V. Okay, that proper subalgebra is what I'm calling capital U. Now let's describe capital U. It turns out that in the Q-shuffle algebra V, the X and the Y satisfy the Q-set relations, as you see there. Okay, so there must be some algebra homomorphism, I'll call it the natural map, from UQ plus into the Q-shuffle algebra bold V that sends the A to the X and the A star to the Y. And just by construction, that natural map has image U, capital U. And it's a non-trivial fact, but according to Rosso, that natural map from UQ plus to U is an algebra isomorphism. It's automatically surjective, but to show injectivity, takes a good deal of work, and that was due to Rosa. All right, so that subalgebra U, that's isomorphic to UQ plus. We can think of it as a copy of UQ plus sitting inside the Q shuffle algebra bold V. Now, to illustrate how useful that is, let's apply the natural map to the Damiani PBW basis for UQ plus. Let me give the two letters X and Y a weight. The weight of X will be 1, and the weight of Y will be -1. Now, suppose we're given a word, V1, V2 out to Vn. I'll call it Catalan whenever all the partial sums of weights, V1 bar plus V2 bar up to Vi bar, is non-negative for every I, 1 to n minus 1, and 0 if I is equal to n. And in this case, that the n has to be even. So, for example, for n up to 3, I've written out there the Catalan words of length 2n. So length 0, just the identity, empty word 1. Okay, length 2, xy, length 4, xy, and xxyy. And length 6, because you see the 5 Catalan words of length 6 at the bottom there. And if you're familiar with the Catalan numbers, the nth Catalan number counts the number of Catalan words of length 2n. So 1, 1, 2, 5 is how the sequence of Catalan numbers starts out. Okay, now using these Catalan words, I'm going to define some elements in the bold V vector space that I'll call Cn. So for any natural number n, I'll define Cn to be a certain weighted sum of all the Catalan words of length 2n. So given a Catalan word of length 2n, V1, V2 out to V2n, the coefficient is a product of these Q integers. And you can see from the display there that the product involves the partial sums of weights. So, V1 bar plus V2 bar up to Vi bar for some I. Okay, adding 1 in order to ensure that it's a positive integer, and then take the Q integer of that. Okay, anyway, so Cn is this weighted sum of all these Catalan words of length 2n. So for example, coming back to the n at most 3, I show the corresponding Cn's. So C1 is a scalar multiple of xy. C2 is a linear combination of xy and xxyy, and so on. Okay. Now, what makes these Cn elements remarkable is that natural map takes En delta plus alpha naught into a scalar multiple of the free product of x and Cn. It takes En delta plus alpha 1 into the same scalar multiple of the free product Cny. And it takes the En delta elements into another scalar multiple of just Cn. Okay, so in other words, via the natural map, we can express the Damiani PBW basis for UQ plus in closed form in terms of the Cn elements. Okay, now recall that Q shuffle algebra bold V. I'm going to introduce a type of word now in bold V said to be alternating. These alternating words are defined as follows. So start with the word V1, V2 out to Vn in bold V. I'll call it alternating whenever n is at least 1 and Vi minus 1 is not equal to Vi for I2 to n. So in other words, the alternating words have the form just back and forth, xy, xy, forever. depending on how the word starts and ends, we get 4 types of alternating words. The alternating word might start and end with X, in which case we get X or XYX or XYXYX, etc. Or it might start and end with Y, giving us Y or YXY or YXYXY, etc. Or it might start with Y and end with X, YX, or YXYX, etc. Or the other way around, start with X and end with Y. So we get naturally four types of alternating words. Okay, now I showed a few years ago that the alternating words in bold V are actually contained in U. Remember, U was the subalgebra generated by the X and the Y with respect to the Q shuffle product. So that's a non-trivial fact that those alternating words can actually be expressed as polynomials in the X and the Y using the Q shuffle product. Okay, now let's come back to Roseau's algebra isomorphism, the natural map from UQ plus to U. Let's define an alternating element of UQ plus to be a natural pre-image of an alternating word in bold V. Of course, that'll be in U. Okay, so we're pulling back, so to speak, the alternating elements in U, pulling them back to UQ plus, and whatever we get, we're calling that an alternating element of UQ plus. Let's give those alternating elements of UQ plus some names. So let's arrange it so that the map natural sends W naught to X, W minus 1 to XYX, W minus 2 to XYXYX, etc. And have it send W1 to Y, W2 to YXY, W3 to YXYXY, etc. G1 will go to YX, G2 will go to YXYX, etc. And G1 tilde will go to XY, G2 tilde will go to XYXY, etc. Okay, now remember the A went to the X and the W naught is going to the X. So W naught is equal to A, and similarly W1 is equal to the A star. Okay, so our next goal is to describe the relations between the alternating elements of UQ plus. And as we'll see, there are 2 types of relations. For notational convenience, let me define G naught to be 1 and G naught tilde to be 1. Okay, here are the relations of the first type. For any natural number K, the following relations hold in UQ plus. The commutator of W naught and WK plus 1 is equal to the commutator of W minus K and W1, which in turn is a scalar multiple of GK plus 1 tilde minus GK plus 1. And then we have some relations involving the Q commutators, W naught and W1. Okay, looks roughly similar to what we saw at the level of UQ plus, but the details are a little bit different. The scalars a little bit different on the right-hand side. Okay, and then we have some more relations, and these relations are identical to the corresponding relations that held for UQ plus. Okay, so we're encountering a situation in, I said UQ plus, I should have said OQ. We're encountering a situation in UQ plus and OQ that are, or CalOQ that are, quite analogous. Okay, now let's recall the alternating central extension, CalOQ, of the Q-Onsager algebra OQ. So those relations type 1 and 2 that I just showed you, they closely resemble the defining relations for CalOQ. So let's seek an algebra CalUQ plus that's related to UQ plus in the same way that CalOQ is related to OQ. And we'll use the above relations of type 1 and type 2 to define CalUQ plus. Okay, so we'll define an algebra CalUQ plus now by generators and relations. The generators are W minus K, WK plus 1, GK plus 1, GK plus 1 tilde. And the relations are the relations of type 1 and type 2 from the previous slides. So those generated will be called alternating, and we'll call Cal UQ plus the alternating central extension of UQ plus. Okay, so my next goal is to describe how UQ plus and Cal UQ plus are related. And to describe this relationship, let me bring in some polynomials now. So let Zn, n1 to infinity, be mutually commuting indeterminates. And let f bracket z1, z2, and so forth be the algebra consisting of the polynomials in all those z's that have coefficients in the ground field f. And let z0 be 1. Okay, so I proved a year or so ago that there's an algebra isomorphism, phi, from Cal UQ plus to the tensor product of UQ plus and this polynomial algebra in infinitely many variables that sends W minus n to the sum over k 0 to n of WK minus n tensor ZK, and something similar for the other alternating generators, the Wn plus 1, the Gn, and the Gn tilde. So as a special case, the W0 goes to W0 tensor 1, and W1 goes to W1 tensor 1. Okay, now I just gave an algebra isomorphism phi from Cal UQ plus to the tensor product of UQ plus and this polynomial algebra in infinitely many variables. So next, let me describe some consequences of this isomorphism. Okay, so let brackets W0, W1 be the subalgebra of Cal UQ plus generated by the W0 and the W1. Okay, then I showed a few years ago that there exists an algebra isomorphism from UQ plus to brackets W0, W1 that sends the A to the W0 and A star to the W1. Okay, so in other words, brackets W0, W1 is a copy, if you will, of UQ plus. Okay, let's talk about the center Z of Cal UQ plus. It's generated by an infinite sequence of elements, Zn check, n1 to infinity, where Zn check is given by that rather complicated looking expression that you see there, in a weighted sum involving products of G's and G tildes and W's of negative type, W's of positive type. Okay, now it turns out that for every positive n, that the isomorphism phi sends this Zn check that we just looked at to the tensor product of 1 and lowercase zn check, where the lowercase zn check is simply the sum over k 0 to n of the indeterminate zk times zn minus k times q to the n minus 2k. Okay, so the Zn checks, the lowercase Zn checks, those are algebraically independent. That's not hard to show. And as a consequence, those central elements, the capital Zn checks, are also algebraically independent. Okay, now for the algebra Cal UQ plus, we've got two natural subalgebras, namely the brackets W0, W1, and the center, the Z. And they're related in the following way. So using the multiplication map, the tensor product of brackets W0, W1 and the center Z get sent to Cal UQ plus in a bijective fashion. W tensor Z going to the ordinary product of WZ. Okay, and as a consequence, the Cal UQ plus algebra is generated by the W0 and the W1 together with the center Z of Cal UQ plus. Okay, so this is all starting to look very much like the Cal OQ observations that Baseilhac and Shigechi made. Okay, one more point about CalUQ plus. A PBW basis for CalUQ plus is obtained by the alternating generators, the G's, the W's of negative type, the W's of positive type, and the G tildes in any linear order that puts the G's first, followed by the W's of negative type, followed by the W's of positive type, followed by the G tildes. Okay, now we just gave a number of results about UQ plus and CalUQ plus. Viewing UQ plus and CalUQ plus as toy models for OQ and CalOQ, we were able to obtain similar results for OQ and CalOQ. However, OQ and CalOQ require very different proofs because there's no Q-shuffle algebra realization available for those, at least that I'm aware of. So in the next few slides, I'm going to summarize our results for OQ and CalOQ. Okay, so first of all, a PBW basis for CalOQ is obtained by the alternating generators, the G's, the W's of negative type, W's of positive type, G tildes, in any linear order that puts the G's first, followed by the W's of negative type, followed by the W's of positive type, followed by the G tildes. Okay, that result we proved using the Bergman-Diamond lemma. Okay, next, let brackets W naught W1 be the subalgebra of CalOQ generated by W naught and W1. Then there is an algebra isomorphism from OQ to brackets W naught W1 that sends the A to the W naught and A star to the W1. Now to describe the center Z of CalOQ, I'll bring in some generating functions. B of t, in that indeterminate t, recall, B of t is this power series, sum over n, 0 to infinity, of Bn delta coming from that Baseilhac Kolb PBW basis, times t to the n. Gn tilde generating function is a similar power series with coefficients, the Gn tildes. Okay, now back to the center Z of CalOQ. It's generated by some elements, Zn check, n1 to infinity, that are defined in the following way, using a generating function. Their generating function, Z check of t, satisfies Z check of t is equal to a scalar zeta there, times G tilde of capital S times B of t times G tilde of capital T, where the capital S and capital T are these fractions that you see near the bottom there, involving that earlier indeterminate, the T. Okay, and the zeta constant is at the very bottom. Okay, so the details are slightly complicated, but the general form of we got this nice relation, the nice product formula that gives the Z check of t generating function that we can then use to work out the coefficients, the Zn checks themselves. Okay, upshot, the Zn checks are algebraically independent. And in the algebra CalOQ, the subalgebras brackets W naught W1 and the center are related in the same sort of way that these subalgebras were related for CalUQ plus. In other words, the multiplication map takes us from the tensor product of brackets W naught W1 on one side and the center Z on the other side over to CalOQ in a bijective fashion, sending W tensor Z to the product WZ. Okay, now I'm shortly going to give you a few more results about OQ and CalOQ. But first, let me introduce the alternating elements of OQ. Now, let me emphasize, just from the definition of CalOQ, the generators, the W minus Ks, et cetera, those were the alternating elements. So far, we don't have corresponding elements in OQ, but now I'm going to introduce those elements. Okay, so it goes like this. There's a surjective algebra homomorphism, I'll call it gamma, from Caluq to OQ that sends the W0 generator to A, W1 goes to A star, and the Zn checks all go to 0. So I'm effectively, killing off the center of Caluq and looking at what's left, the W0 and the W1, or if you like, the A and the A star, and those generate a copy of OQ. Okay, now using the gamma map, we can define some elements in OQ denoted W minus K, WK plus 1, GK plus 1, GK plus 1 tilde. Those are just the elements obtained by applying the gamma map to the alternating elements back in Caluq. So again, we've got these alternating elements in Caluq. We've got this algebra homomorphism gamma from Caluq to OQ. We just apply that homomorphism to all the alternating elements and get some elements in OQ, which we're now calling the alternating elements of OQ. Okay, and now using those alternating elements, we get an algebra isomorphism phi from Caluq to the tensor product of OQ and that polynomial algebra in infinitely many variables that sends each W minus N to the sum over K, 0 to N of WK minus N tensor ZK, and similar for the other alternating elements. Okay, entirely analogous to what we saw earlier for UQ plus. Okay, now just a few more points. Referring to Caluq and a positive N, the isomorphism phi sends the central element Zn check to one tensor lowercase zn check, where the lowercase zn check is defined as follows. So using generating functions, its generating function z check of t is related to the generating function z of t in the following way. So z check of t is equal to the product of z of capital S, z of capital T, where the capital S and the capital T were those fractions involving the indeterminate lowercase t that we saw a few slides back. Okay, so that's the end of my description of how OQ and Caluq are related. Let me finish with an open problem. There's a linear algebraic object in the literature called a tridiagonal pair. And a tridiagonal pair of Q-Rock type is essentially the same thing as a finite dimensional irreducible module for OQ, the Q-Onsager algebra, on which the generators, the A and the A star, are diagonalizable. Tridiagonal pair consists of two linear transformations that are diagonalizable, and they each act on the eigenspaces for the other one in a block tridiagonal way. So each of the maps takes the ith eigenspace for the other one and sends it into the sum of the I minus first, the ith, and I plus first eigenspaces. Okay, that's the essence of a tridiagonal pair. And so this tridiagonal pair of Q-Rock type, I won't get into the precise definition, but certain type of tridiagonal pair comes from the irreducible OQ modules. Okay, so the problem is this. So given a tridiagonal pair of Q-Rock type, how do the alternating elements of OQ, the W minus Ks, the WK plus 1s, the GK plus 1, GK plus 1 tildes, how do they act on the underlying vector space? Or more generally, find the algebraic meaning of the alternating elements for any tridiagonal pair of Q-Rock type. Okay, so in summary, so in this talk, I described how the Q-Onsager algebra, OQ, is related to its alternating central extension, Caluq. And to motivate the description, we first considered a toy model involving UQ plus and its alternating central extension, Caluq plus. And we saw that OQ is related to Caluq in roughly the same way that UQ plus is related to Caluq plus. And we finished with an open problem. Thank you for your attention.
Thank you very much for the very nice talk. So if anyone has questions, you can raise your hand, or if you want, you can type it in the chat. So do we have any questions? Okay.
Yeah,
I have a question.
Okay,
That's a
John,
question
please
also.
go ahead first.
Okay, could you just say something about how this can be applied to solving statistical mechanical problems?
How can all this be applied to solve statistical mechanics, problems in statistical mechanics? I'm actually not the right person to ask that question. I would suggest asking Pascal Baseilhac. I come out of combinatorics, pure algebra, and what I know about statistical mechanics, basically, I learned from Pascal Baseilhac. So he is using Q-Onsager algebra to understand the statistical mechanical models. So he's, I consider him the world expert on this particular topic. He's deeply into it. The general idea is that, and I just know the buzzwords. I don't understand the details, but somehow the Q-Onsager algebra is used to solve integrable systems that involve a boundary on which you are reflecting. Stuff is getting reflected. As I understand it, this RK reflection equation is designed to sort of handle this boundary with reflections. And somehow the Q-Onsager algebra plays a role in that.
So these spin models or icing models, or I'd just like to have an idea of where the physics application comes.
Well, frankly, I also would like to know better what the details of the physics applications.
They arise, John, in spin models and with boundaries, and it's just Q generalization, anisotropic generalization. Onsager introduced his algebra for the Ising to solve the Ising model. And you can imagine that deforming the Ising model will bring the Q deformation of the Onsager algebra and onwards. But we'll have Pascal Baseilhac, as you know, John, will be is organizing a workshop in our semester-long program. You'll have ample time to ask this question with him. Paul, I'd like to congratulate you for, it's an involved algebraic topic that you presented to us very clearly with all its intricacies. So I've really, for one, much enjoyed your talk. Let me ask a fairer question. In your alley, what importance, so you started by indicating that this is also rooted in the algebra, could you comment on the use that these results would have for you in the algebraic combinatorics, and in particular, for instance, the question you asked, the open problem you described, knowing how these alternating generators would act on a tridiagonal pair of Q-Raka type. What would this give?
Yeah, okay. So now I'm on the firmer footing. So Baseilhac, comes out of statistical mechanics. I come out of a very different tradition: combinatorics, algebraic combinatorics, and related topics such as quantum groups and Lie theory and special functions. So playing around with algebraic graph theory, a highly regular type of graph called a distance regular graph. Years ago, so this is back in the 80s, I just monkeying around, I discovered that the adjacency matrix together with a certain diagonal matrix acted on each other's eigenspaces in this tridiagonal fashion. And I thought, well, that's odd. How could two matrices do this to each other's eigenspaces? And I was fascinated by it, and I pursued it for multiple years. And after an embarrassingly long time, I realized you didn't actually need to start with a graph. You could just talk about abstract linear transformations that acted such and so on each other's eigenspaces. That led me to the notion of a tridiagonal pair. Around the early 90s, I discovered that any tridiagonal pair, A star, satisfied the tridiagonal relations. That led to the connection to quantum groups. Playing around with those relations, I started showing those relations to various people. One of the people that I showed them to was Georgia Bankart, a Lie theorist in my department. And she said, oh, that special case where you have 0 on the right-hand side, those are the Q-Ser relations. That was the first time. At that point, I knew nothing about quantum groups. I had never heard the phrase Q-Ser relations before. That was around 1995. So the old timers know this, but let me just emphasize, the whole subject of quantum groups is not that old. When I was in graduate school, so we're talking the early 80s, this was something for the future. Drinfeld introduced the quantum group concept to the general mathematics community at the World Congress of Mathematicians in the late 80s. So, during the 90s, it was the theory of quantum groups was going great guns, and people were developing it at a very rapid clip. And at some point in there, mid-decade, I first heard about it, and then I discovered, with the help of Georgia Bankart, that there was this connection to these tridiagonal relations that I had been working on. So that, let's just say, gave me a huge motivation to learn quantum groups. And so I started reading about that, and in short order, I started teaching graduate courses on the topic. And since then, I've taught, I don't know, dozen courses on quantum groups of various types. Anyway, so one thing led to another, and okay, here we are. Now let me come back to the graph theory. From what I've said, so the tridiagonal relations, okay, the most general case, the Q-Dolan-Grady relations, those are the defining relations for the Q-Onsager algebra. And back at this level of distance regular graphs, that original setup, the adjacency matrix A, and then this diagonal matrix A star, we can consider the algebra that they generate, and that's called the subconstituent algebra.
The Terwilliger algebra.
It's all, so my graduate students call it the Terwilliger algebra. I'm still embarrassed to call it the Terwilliger algebra. So anyway, yeah. the two names have been kicking along in parallel. Okay, anyway, so this T algebra is in this general, the Q-Raka case, it is a homomorphic image of the Q-Onsager algebra. Or if you like, the underlying vector space, usually called the standard module, which has the vertices of the graph as a basis, is a module for the Q-Onsager algebra in a natural way. So the two generators for the Q-Onsager algebra, the W0 and the W1, or the A and the A star, they act on this module such that, you know, the one generator becomes the adjacency matrix and the other generator becomes this certain diagonal matrix. And they're acting on each other's eigenspaces in this block tridiagonal way. Now that standard module, it's not an irreducible module, but it's semi-simple. It decomposes into a direct sum of irreducible modules. And on each of those irreducible modules, the generators, the W0 and the W1, act as a tridiagonal pair. So if we can thoroughly understand the tridiagonal pairs, then we can understand the irreducible modules for this Q-Onsager action on the standard module of this distance regular graph. So that in a nutshell was what, you know, motivated me and the people around me to thoroughly understand tridiagonal pairs in the abstract. Not just that, I mean, that was the initial motivation, but after a while, we kept seeing new kinds of applications come into the picture. And we realized that what we were looking at had, you know, wider applicability than just back at the level of algebraic graph theory. And then when Baseilhac came in with the statistical mechanics connection, then that kind of, you know, blew us out of the water, and we realized that we're dealing with a much bigger fish than we had originally realized. Let's put it that way.
Thank you. Thank you very much, Paul.
Okay, thank you.
Ivan, go ahead with your question.
Do we still have time for one more question?
Yes, please go ahead.
So Paul, you'll have to correct my memory if I'm wrong, but I think you classified the irreducible of OQ, the irreducible modules.
So around 2012, my two co-authors, Kazumasa Nomura and Tatsuro Ito, and I classified up to isomorphism all the tridiagonal pairs for any Q, not just the ones that are fail to be a root of unity. That's correct.
So do you think that the problem of classifying the irreducible for Cal OQ, where the center is non-trivial, I mean acts not as zero, is something doable, or is it overwhelming? The center is infinite dimensional, right?
Correct. So that center is isomorphic to a polynomial algebra in infinitely many variables, the Z1, Z2, and so forth. Now, this alternating central extension, so as an algebra, it's isomorphic to a tensor product of the original Q-Onsager algebra on one side, and on the other side, this polynomial algebra in infinitely many variables. So when we consider the irreducible modules for this alternating central extension, in some sense, they're kind of trivially related to the irreducible modules for the Q-Onsager algebra, because the Q-Onsager algebra side of the alternating central extension, behaves the same, from the two viewpoints. And on the other side, considering the polynomial algebra, well, that's a commutative algebra. You can just set those variables, the ZNs, to whatever scalars you like, and they're going to act, just as scalars on whatever is your irreducible module.
In other words, you just choose the number they're acting with.
Yeah.
So the problem is rather trivial.
So yeah, in the abstract, the problem is kind of trivial. But in the the specific applications where you have not every possible irreducible module, but just some specific one showing up, okay, then you can ask, well, okay, for the ones that show up, what is the meaning of, so the z's are assigned to some scalars. What scalars are those, and why did they get assigned to those particular scalars?
Well, in the case of physically relevant algebra where there's a center, very often the algebra or the representation comes with an inner product, and you want the action to be self-adjoint or unitary, and that usually makes the center or the study of the centers highly non-trivial.
Yeah, okay. For the Q-Onsager algebra, there is if you take a finite dimensional irreducible module, there is a natural bilinear form on that module that with respect to which the two generators, the A and the A star, are invariant. So this means if you take two vectors u and v, let's say, in the module, then AU comma V, the inner product of AU comma V is the same as U comma AV. So you can pull the A from one side to the other. And also for A star U comma V is equal to U comma A star V. So this bilinear form is quite useful at times. It's nice to be aware of its existence, and that form should be there at the level of the universal central extension as well.
Thank you.
Do you have any final questions? Well, if not, let's thank Professor Terwilliger again for a very nice talk. Thank you very much.
Thank you very much.